Hi, I'm Ramesh, and I will be discussing about the topic of pressure drop across complex geometries when there is an oscillating flow, mainly focusing on the regenerators of the Stirling engine. So this is the paper given to me, and these are the original authors. And we will be talking about some overview of Stirling engine and the literature review for this paper and the conclusions and the recent research that has been done based on this paper. So, so a quick overview about the Stirling engine is that these are external combustion engines that can be powered by a wide range of heat sources such as thermal based and biofuels. So, since it can be powered by a wide range of heat sources, this has the high potential to elevate some of the increasing global demand for clean energy. Since since the recent generation is talking more about clean energy, this can be useful. So, a lot of research has been going on in this Stirling engines. So, the important part of this Stirling engine is the regenerator part, which is which main purpose is to exchange thermal energy with the working fluid after each isothermal expansion and compression stroke of the engine. So you can see the working of basic Stirling engine here. So this is the early Stirling engine developed. So now the design has been changed multiple times. So the main characteristics of an effective regenerator is it has to have a high thermal storage capacity and heat transfer capacity after each thermal and isothermal expansion and compression stroke, and it has to have a limited pressure drop across them, and it has to have a sufficient temperature distribution. So this is a basic Stirling engine, and this is the part we are focused on this paper. So what will be the pressure drop across this, and how will the regenerator uh, involved? So coming to the literature part, so this is the part majorly focused on um, the pressure drop across the pistons. So the literature survey is chronological in order, starting from early 90s. So though before early 90s, so there are data available for the pressure drop based on this steady flow assumptions. But there will be cases of oscillatory flow in any Stirling engine and other respiratory flows. So we have to study the effect of oscillatory flow and the pressure drop because of that. So few people uh, few people analyzed the oscillatory flow conditions and measured the flow friction and heat transfer characteristics of various type of regenerator. So this regenerator you saw in the previous slide can be of many shapes and sizes. So it can be made of many materials. So we have to analyze the pressure drop across the regenerators. So they found that the pressure drop loss in the Stirling engine regenerators cause the maximum loss in output power. So we have to, once we measure it, we can improve it. So and they found that pressure drop for various regenerator materials, they analyzed for wire netting, sponge metal, and stinted metal. So they found that it can be these pressure drop values can be estimated by using the hydraulic diameter as the representative dimension. So you might have seen in Reynolds number there is a characteristic length, and so that characteristic length should be taken from the hydraulic diameter based on the engine. So a few other people came and they have done a series of experiments, and based on those experiments, so they did a pressure drop analysis of the oscillatory flow in packed columns, and found that these values are 4 to 6 times higher than the values they got from the steady flow assumption. So since they are very far off, so we have to gather more data to measure it and improve its efficiency. So they also found at a small Reynolds number, the pressure drop ratio depends only on the geometry of the regenerator, and it is independent of the kinetic Reynolds number and hydraulic diameter. So we will discuss about this kinetic Reynolds number later. So few other people came and they made their own Stirling engine setup. It is very easy to set up a basic Stirling engine, and they generated the oscillatory flow from a linear compressor with the frequency of 50 Hz. So what they found is the results reveal that the average pressure drop over a cycle in the oscillatory flow through regenerator is 2 to 3 times greater than the steady flow based on the steady flow assumptions. So these people have built the oscillatory flow for this frequency, and they found this results. It is 2 to 3 times greater than the steady flow assumptions. One of the interesting study is that one person has studied the effect of pressure drop when the oscillatory flow is open to atmosphere. That is the infinite space when from two-channel column. So he found that when fluid flows through a system to open to an infinite space, energy is lost to viscous dissipation effects, including boundary layer turbulence and random motions, so which are known as head losses. So he also found that there are another minor losses happening because of pipe bends, walls expansions, the entrances, and the geometry of the exits also. So these are called minor losses. So when even though there are some data on head losses, there are very few data on minor losses, and he found that this minor losses uh, in the oscillating flow dissipate acoustic power and create pressure gradients, so which will result in the power dissipation. So it will reduce the performance, and it has to be reduced. So based on these data, this paper has done a series of experiments from the Stirling engine. They have made few obstructions like these, and they have developed oscillatory flow based on from the Stirling engine. And the results they found is the maximum pressure drop of the oscillatory flow increases with increasing piston frequency. So these are the formulas for the pressure drop. This is a non-dimensional pressure drop, and this is the kinetic Reynolds number. As you can see, the maximum pressure drop is increasing piston frequency is since this omega is in the numerator, it is also proportional. So the physical phenomena they found is the pressure drop is mainly due to the gas inertia of the when there is no obstructions in the there is no regenerators, like, so there is no obstruction between the pistons, and when there are obstructions, the pressure drop is mainly due to three losses: inertia, frictional, and local losses. Local losses in the sense it is also called as minor losses. So they concluded that so the dimensionless pressure drop and the kinetic Reynolds number are inversely proportional. So as you can see that the velocity term is in the denominator, and it can also affect the Reynolds number. So later after this paper came out in 2004, and a few studies have been done based on this paper also. So the work by Delay concluded that experimental investigation involving a regenerator constructed using arrangement of pillars. He has made this arrangement and analyzed oscillating flow conditions, what is the pressure drop, and he has formulated few link between parameters. So he correlated that pressure drop and parameters like porosity, frequency, and frequency of the piston stroke is also related. And he also compared it with steady flow assumptions calculation and found the friction factor is greater than the steady flow assumptions. So we have to gather more data on oscillatory flow specifically. So one of the interesting paper I found is there is a parallel study on the nasal airflow. So the nose through our nose revealed that the steady flow assumptions cannot be relied upon after this, and they also found that transient flow are more predominant in the nasal flow because it is a oscillating flow, and this transient flow inclusion will produce more accurate results of even when there is a low Reynolds number. Yeah. These are the references I used for this paper, and thank you.